Now from here, all the theoretical explanation or all the explanation we've been doing since morning, this is where we are going to implement it. This is where we are going to what? Implement it. Right? Now, you are now going to see the main reason why you need to understand those freely expanded, prevented expansion, partially expanded. Now, the last expansion, the last type of expansion, which is what? If the expansion is partially prevented, I said you have two formula. You have two formula. Any of these formula works. This is the first one. The stress is induced when it is partially prevented. For your first formula is telling you that the Young's modulus multiplied by linear expansivity times change in length times the allowed expansion divided by the original length.
Everything.
Yeah. This guy multiplied by all of this. That's your first method. Or that's your first formula when it comes to partially prevented. Number two is that your strain multiplied by Young's modulus. How do you get, given from the question, from that question, you are giving Young's modulus, right? Yes. But are you giving strain? By formula, what is strain? Change in length over original length. But in this case, partially prevented. So it is not the usual formula for strain that I know, which is change in length over the original length. This becomes the formula. The prevented expansion or divided by the, it's still the same thing though. This is the prevented expansion, right? When we say prevented expansion, meaning the total length minus what you are preventing, right? So you are saying the prevented expansion or divided by the original length. The question is, how do you get this prevented expansion? Use this formula. Total length minus what? Prevented expansion. Now read the question given. The question says that, I've already said it. I said, given any question, assimilate, understand. Given this question, what am I giving? What do I need to calculate? Right? Now, given this question, don't mind, though you are going to mind it in this case, because that's the basis of the formula you are using. But regardless, focus on the parameters. Focus on the value of the parameters. Then you are good to go. Now, let's read this question together. The question says that what? A period of what? Of 15 meter long. 15 meter long is at a temperature of 15 degrees. Of 15 degrees Celsius. Find the free expansion of the length when the temperature is raised to what? 65 degrees Celsius. Now, initially, before the raising of the temperature, when we say raise temperature, meaning change in temperature, before that temperature changes from the initial temperature to the final temperature, initially, that body has a temperature of what? 15 degrees Celsius. Now, the type of that temperature, what we call it, I forgot to tell you guys before. You having a material, that material has its self temperature, and it is called ambient temperature. Any question? So meaning initially the ambient temperature in that, this is steady, right? Meaning initially the ambient temperature is given as what? 15 degrees Celsius, and this particular temperature is raised to what? 65 degrees Celsius, right?
Yeah.
So question now says that calculate the free expansion. Calculate the free expansion. Now, though not necessarily, but you should be able to do that. It shows that you know what you are doing, and at the same time, it shows that you have better understanding of what you are doing. So you can illustrate, since you understood case 1 and case 2 from what we explained, so you can illustrate this question using diagram. So, but before the diagrammatical explanation or illustration, let's list out the parameters. What we are given, let's list it out. So, solution, giving, what are you giving? Solution, you are giving the length to be what? 15 meter. You are giving T1 15 degrees Celsius. You are giving T2 65 degrees Celsius. Question says that calculate the free expansion of this what? Rod. Right? That's the question, right? Or what's the question?
Find the temperature space. Find the free expansion of the length.
All right. Find the free expansion of the length when the temperature is raised to 65 degrees Celsius. Now, out of all these formulas, or out of all these formula we've derived so far, which one am I using? Or this particular question, what scenario can you relate it to? Is it case 1? Is it case 2? Is it case 3? By case 1, what is case 1 saying? Free expansion. Meaning when this stress is induced, we have it increases, right? It increases just because it is not fixed. That's what we are saying. Are you getting me? So if you are meant to, like, if personally, if you say you want to draw diagram, it's something that you can just do. But okay, let's say you want to draw diagram. This should be your expected diagram. Say initially you are having T1. What's T1? 15 degrees Celsius. What's T2? 65 degrees Celsius. Right? What else? The length. What's the length? The length is what? 15 meter. So this is your illustration. So you can do this as well. This is what you have to calculate. The change in length. Right? From here, giving. You are giving Young's modulus as what? What's your Young's modulus? And what's your Young's modulus is equals to what? 200 giga Newton per meter square. What's your linear expansivity? 12 times 10 raised to power -6 per degree Celsius. Right? That's all. That's what we are giving. So recall what's the formula for change in length? Recall change in length for free expansion is equal to linear expansivity times length. Call this one. This implies that change in length times L all into bracket T2 minus T1. Input values, what do you have? Therefore, change in length becomes before your substitution, watch out for the unit of your parameters, or you say of your data. The unit must correspond to the unit of your Young's modulus. What did I say? The unit of your length or of any parameter either must correspond to the unit of your Young's modulus. Now, meaning that for up to this level, can I substitute directly without doing any conversion? Can I? Can I? Yes. My length is a meter. My Young's modulus is also in what? Meter. In a case where I'm having millimeter, what will happen? I will convert. Always watch out for that. Very, very important. So input value meaning substitute. By substitution, it becomes what? 12 times 10 raised to the power of -6 multiplied by, what's your length? 15. Right? Multiplied by change in temperature. What do you have? What do you have? 65 minus 15. 65 minus 15. By the time you put all this in your calculator, meaning 12 times 10 raised to the power of -6 times 15 times what? 50. What's the answer, please? Change in length becomes what? Right? Or 9 millimeter. Why do you say 9 millimeter? Multiply by 10 raised to the power of 3. Alright. Any questions so far? No question. So what it means is that the stress, let's say these stresses have been reduced due to this heat, right? This heat subjected to this particular rod. So the increment or the expansion that the stress that has occurred or that has induced can cause in increment is only what? 9 mm. It can't produce more than 9 mm or less than. Are you getting me? It can't produce more than 9 mm or less than 9 mm. Now imagine, or now let's say you don't have the idea of free expansion. It becomes a problem. What did I say? You don't have the idea of what free expansion means. It becomes a problem. Meaning, what are you using? So can you now see how we related what we learnt or what we've known to question giving. Any question so far? No question. All right, this is just the first example. Number two says that what? Find the temperature stress produced when the expansion of the rod is prevented. Keyword. Now, when we say prevented, meaning that I have this guy fixed, right? Meaning this initial expansion, which is 9 mm, cannot be achievable, meaning we can't have it regardless of the stresses induced. Now, what is the formula for prevented expansion? The stress of prevented expansion. What's the formula? Linear expansivity times what? Times what? Times Young's modulus. Times Young's modulus. Or you say modulus of rigidity. Modulus of rigidity. Now, input values. What's your Young's modulus? 20 giga-Newton. Okay, 200 giga-Newton per meter square. When you say giga? Mega. Kilo. Nano. Pico. Farad. Let's continue. Alright. Now from here, we then have what? What do you have, please? Call this for me. This becomes what? Roman figure 2. Or should you list out this value? Okay, let's do that. 12 times 10 raised to the power of negative 6 per degree Celsius, right? Change in T. We've calculated it. 50 degrees Celsius, right? Young's modulus 200 giga-Newton per meter square, or you say gigapascal. So, meaning from Roman figure 2, by the time we substitute all this, we then have 12 times 10 raised to the power of negative 6, right? Multiply by what? 50. Multiply by what? 200 times 10 raised to the power of 9. 200 times 10 raised to the power of 9. So let's input this in our calculator. What's my answer? Your answer becomes what? The stresses, when it is prevented, is what? 0. Okay, 120 mega Pascal. That is 120 times 10 raised to the power of 6 Newton per meter square. Or let's express in giga. What do we have? 0.12 giga Newton per meter square. Any question on this? Any question? Yes. All right. This is we've been solving a particular question since morning, right? So the first question, we've done that, free expansion. The second question, prevented expansion. This is what we got. Now, from here, what's the last one? When the expansion is partially prevented. Prevented by what? By 6 what? Millimeter. Now, it is your choice, right? I said, when it comes to partially prevented expansion, we have 2 formulas. This is the first formula, and this is the second formula. Whichever one you feel like it is easier for you, make use of it. What did I say? Make use of it. Alright, we are going to, for this very question, or for this particular question, I'm going to use the 2 formulas. I'm going to make use of the first one, and I'm going to make use of the second one, just to confirm if you are going to get the same answer. Just to what? Confirm if you are going to get the same answer. Now, what we just need to do from here is to what? Input values, substitute values. By substitution, what do we have? The last one. When it is partially prevented, I'm having my formula as this, right? What's my E? At this level, please, let's do it together. So, what's my... Do we still need to write those values out? No, let's substitute directly. So I'm having what? What am I having? The stresses induced for partially prevented, it becomes what? Following equation 1, what do you have? You are having Young's modulus. What's your Young's modulus? 200 times 10 raised to the power of 9. All into bracket, your linear expansivity, 12 times 10 raised to the power of minus 6, right? Multiplied by what your change in temperature, 50. Check, identify. What is the allowed expansion? 6 what? Read the question. Read Roman figure 2 again.
What is permitted to expand by 6 millimeter? That's allowed.
Allowed expansion. Allowed expansion. Can you now see how it works? Allowed expansion. But in that case, I'm having what? You know, initially the total length is what? 9 meter. But they said allowed, permitted with this particular value, which is what? 6 millimeter. But in this case, the expansion is in what? Mm. But I'm working in what? Meter. So convert. By the time you convert 6 mm to meter, what do you have? 0.006. Right? So I'm having what? Times 0.006 all divided by what was your length? 15. So press this, input this value in your calculator. Tell me your answer. What's delaying us now is just to confirm if this value is correct. Then we should proceed. Is this value correct? This one, your answer, this answer minus this 0.002. That's what my calculator is giving me. Get the value, get this value, keep this value, get this value, keep it, then minus. I believe you are getting the same thing, then we proceed. 12 times 10 raised to the power of negative 6. 0.30. Okay, 30. It is 30, right? 0.0002, right? So are we good to go now? We are getting this value. I'm asking a question. It's giving me syntax error. Use a proper calculator. It's still the same thing. 2 times 12 to minus 4. Alright. What I just want now is that from here, we are getting this value. Are we all getting this value? So we can proceed, right? So alright. Now we said partially prevented, right? Partially prevented. So by partially prevented, you are making use of this formula. Change the multiplication to negative. So meaning that by the time you substitute all your value, get the value of this, get the value of this, subtract, you must get this. This is what you get. Now the product of this and this will give you what? This will give you what? 40 megapascal. Meaning that 40 mega Newton per meter square. This is when you use the first method, or you say the first formula. From here, we said we have 2 methods, right? The first one is what? Make use of this very guy, which is what? The stress is equals to all this, right? Then the other one is what? Prevented over original length. Prevented over original length. So you can just try that on your own and get a value. So if you get a value, your value should be equal to this. But don't worry, I will solve it. I'll pin it in the comment section. So you see how I solve it. So we are done for today.